Hi everyone, I hope you are doing well and welcome back to the AI Tech Explained Right channel, the place for AI professionals and enthusiasts to stay updated with AI advances. In this video, I will talk about TinyLlama, which is an open source small language model. So, TinyLlama is a compact 1.1 billion parameters language model pre-trained on around 1 trillion tokens for approximately 3 epochs, built on the architecture and tokenizer of Llama 2. TinyLlama leveraged various advances like flash detention, which achieved better computational efficiency, and despite its relatively small size, TinyLlama demonstrates remarkable performance in series of downstream tasks, and it significantly outperforms existing open source language models with comparable sizes. And the cherry on the cake, the model's checkpoints and code are publicly available on GitHub at the address shown here. So now let's dive a little bit deeper in technical things. So in their work, authors focused on exploring the behavior of smaller models when trained with a significantly larger number of tokens. To do so, they trained the transformer decoder-only model. And this work is considered as the first attempt to train a model with 1 billion parameters using such a large amount of data. In the next few minutes, we will see how TinyLlama surpassed both OPT 1.3 billion and Pythia 1.4 billion parameters in various downstream tasks. Now, let's talk about pre-training. In their work, authors adopt a mixture of natural language data and code data, sourcing natural language data from SlimPajama and code data from Starcoderdata. To give you a little bit more of context, SlimPajama is a large open source corpus created for training language models based on lit-gpt, which is an open source research effort aimed at reproducing Llama's pre-training data, containing over 1.2 trillion tokens. The SlimPajama was derived by cleaning and deduplicating the original lit-gpt. On the other side, Starcoderdata was collected to train Starcoder, a powerful open source large code language model. It comprised approximately 250 billion tokens across 86 programming languages. In addition to code, it also includes GitHub issues and text code pairs that involve natural language. After combining these two corpora, authors have approximately 950 billion tokens for pre-training in total. During training, authors sample the natural language data to achieve a ratio of around 7:3 between natural language data and code data. Let's talk about architecture now. As I already mentioned, the model architecture is similar to the one used in Llama 2, using a transformer architecture with the hyperparameters shown in the table 1, which are the hidden size, the intermediate hidden size, the context length, number of heads, number of layers, and the vocab size. Stay tuned, guys, with my channel by subscribing, as I'm planning to create a video where I talk about the transformer architecture, where I explain all these kind of information. Now, in the architecture, authors used rotary positional embedding to inject positional information into their model. This method has been widely adopted recently and has been used by many mainstream large language models such as Palm, Llama, and Qwen. Authors apply RMSNorm as their normalization technique, which can improve training efficiency. This was additional to normalizing the input before each transformer sublayer in the pre-normalization phase to obtain a more stable training. Instead of using the traditional ReLU nonlinearity, authors follow Llama 2 and combine Swish and GLU for gated linear unit together, which is referred to as SWI-GLU, and this was their activation function in TinyLlama. And last but not least, authors used grouped query attention to reduce memory bandwidth overhead and speed up inference. They have 32 heads for query attention and use 4 groups of key value heads. With this technique, the model can share key and value representation across multiple heads without sacrificing much performance. Now, for speed optimizations, authors use techniques that have shown their effectiveness in many notable works. Let's start with the fully shared data parallel during training. They used this technique to leverage multi-GPU and multi-node setups efficiently. This integration is crucial, guys, in scaling the training process across multiple computing nodes, which significantly improves the training speed and efficiency. Authors also use flash attention too, which is an optimized attention mechanism, which added a critical improvement in their work. The repository also provides fused layer norm, fused across entropy loss, and fused rotary positional embedding, which together play a pivotal role in boosting computational throughput. Now for the xFormers, authors have replaced the fused SwiGLU module from the xFormers repository with the original SwiGLU module, further enhancing the efficiency of their codebase. With these features, they can reduce the memory footprint, enabling the 1.1 billion model to fit within 40 gig of GPU RAM. Now, authors claim that the incorporation of all these elements has propelled their training throughput to 24,000 tokens per second per a 140 gig GPU, when compared with other models like Pythia 1.0 and MPT 1.3 billion parameters. Their code base demonstrates superior training speed. For instance, the TinyLlama 1.1 billion parameters model requires only 3,456 A100 GPU hours for 300 billion tokens compared to 4,830 for Pythia and 7,920 for MPT, which is a big difference. This obviously showed the effectiveness of their optimizations and potential for substantial time and resource savings in large-scale model training. Now, speaking of the devil, let's talk about training. To build their framework, authors were based on lit-gpt. Like in Llama 2, they employ auto-progressive language modeling objective. During the pre-training phase, they utilize the AdamW optimizer with values equals to 0.9 and 0.95 for beta 1 and beta 2. This is kind of standard, guys. They use constant learning rate schedule. They use 2000 warm-up steps to facilitate optimized learning. They set batch size as 2 million tokens. They assign weight decay as 0.1 and use a gradient clipping threshold of 1.0 to regulate the gradient value. And they pre-train TinyLlama with 16 A140 gig of RAM GPUs. Now let's talk about results. Authors evaluate TinyLlama on a wide range of common sense reasoning and problem-solving tasks and compare it with several existing open source language models with similar model parameters. They compared TinyLlama with OPT 1.3 billion parameters, Pythia 1.0 and Pythia 1.4 billion parameters. For the common sense reasoning tasks, as you see in table 2, TinyLlama outperforms the other models on 6 tasks out of 8 and obtains the highest average scores, which is great. Authors tracked the accuracy of TinyLlama on common sense reasoning benchmarks during its pre-training, and as shown in figure 2, generally the performance of TinyLlama improves with increased computational resources, surpassing the accuracy of Pythia 1.4 billion in most benchmarks. TinyLlama has been evaluated on its problem-solving capabilities as well, using the Instruct Eval benchmark, which includes the MMLU to measure the word knowledge and problem-solving capabilities, the BBH to measure the language model's abilities in complex instruction following, the drop for math reasoning abilities, and last but not least, the Human Eval to measure programming capabilities. As you see in table 3, TinyLlama demonstrates better problem-solving skills on 4 out of 5 tasks compared to existing models with the same size. So this is it, guys, for today. Thanks for watching. I hope you liked the video. Don't hesitate to put thumb up if it's the case, and please don't forget to subscribe to the channel to have more videos like this one. Don't hesitate to put a comment if you need more details on any concept about which I talked so far, and see you next time.